Good morning, everyone. We're going to wait just 2 or 3 minutes before we begin the presentation to allow latecomers a little time to join. Good morning, everyone. For those of you just joining us, we're waiting just 2 or 3 minutes to begin to let everyone have a chance to get involved. Well, good morning, everyone. Welcome to Houston Techfest 2020, the virtual edition. Before we get started, I want to make sure you're aware of a feature that will make the session a little more interactive for you. Please make note of the question mark icon in your presentation screen. If you click that icon, it'll open the question and answer feature, which allows you to send the moderator questions, which I'll then present to Michael at the appropriate time. So please feel free to post anytime during the session. We're also excited to let you know that Code Magazine is going to be giving everyone a free subscription, so you can follow the link posted in that very same Q&A section. We're proud to present Michael Bishop, Principal Consultant at Improving, who will be sharing
course. Covers the principles and theory underpinning the Scrum framework and the Scrum Master's role in it. About a week later, we're going to be providing a Professional Scrum Master 2 course, another 2-day certification course. And then at the end of the month of October, we will have a Professional Scrum Product Owner certification course. If you want to take one of these courses, use the code Techfest 2020, that is Tech-Fest-2020. That'll give you a $500 discount off of this price for any of these courses. And we're looking for people. We are hiring some .NET front-end developers who know React, Node, and JavaScript. Also looking for some senior Java developers with Spring experience. A senior full-stack developer, also a junior full-stack developer who is familiar with Microsoft Stack and Angular version 2 or later. A senior .NET developer with some .NET Core and strong back-end SQL skills. Also testing experience, and also a senior .NET developer, a full stack with React or Angular. If you're interested in this, send your resumes to careers@improving.com and be sure to reference the office closest to you. We have 14 of them now, as you can see here on this little map. We have 5 in Texas, so we have a couple in Dallas, 1 in Houston, Austin, and College Station. We also have an office in Atlanta, 2 in Ohio, in Cleveland and Columbus. We have 2 in Minneapolis. We just opened a second one there. We just opened an office in Omaha. We have an office in the Great White North in Calgary. We also recently added 2 offices in Mexico, in Aguascalientes and Guadalajara. So if you're looking for an alternative for offshoring, consider our nearshoring consider our nearshoring option. We have lots of consultants in Mexico who are ready to help, and they're in your time zone or within one time zone of it. So I think it's a great option to keep in mind. And finally, we have a virtual lunch and learn series. These are free every Friday at noon. You can register at improving.com/virtual events. We also have past talks available on our YouTube page. We've been doing this for about 6 months now. It's been very successful, and we're going to keep doing it. Okay, so tell you a little bit about me. I'm a husband to my wife, Weemin. I have 2 twin boys, 11 years old, Sam and Dave. They keep me more than a little busy. I used to work at NASA for many years before I was thrust into the real world and found Improving. I've been here for about 3 years at Improving. It's a great place to work. We don't win these best places to work awards every year for nothing. It's a great place to work. Have various hobbies you see there. I am an evangelist for the greatest piece of software written by mortal humans, Linux. And I'm a language nerd, not just programming languages, but also spoken languages. I love linguistics. Okay, with that out of the way, let's get down to business. So a little over a month ago, I began working for a new client. Now, I am primarily a back-end Java developer. I have some front-end experience, but I basically do Java coding. So day one at the new client, we're told that the client wants us to write code in Go. So I thought to myself, hey, this is a great opportunity to learn Go. Might want to get started with that. So I did. And Go is it's an interesting language. It's kind of like programming in C without getting your hands dirty. Has some of the pointer stuff you see in C, but you don't do pointer manipulation or pointer math or stuff like that. Has some interesting features like Go routines, which are a very lightweight multi-threading model. It has some object-oriented capabilities. It has interfaces, which enables it to support polymorphism. What it doesn't have are classes, which means it doesn't have subclasses, which means there's no inheritance. So if you do a search on the web about how to implement inheritance in Go, you'll find some articles and posts, well, like I did, that say, hey, use composition. You can do that. We can do it with composition. Well, not really. I mean, you can't do it with composition alone. Composition models composition. Inheritance models inheritance. There's, the has-a and is-a relationships are quite different things. But you can, starting with composition, build something that looks like inheritance when it's viewed from the outside. Even looks like it behaves like inheritance. And the key to doing this is something called delegation. Now, delegation and inheritance are quite different in terms of their mechanisms for deriving behavior. As you all know, in inheritance, objects derive their behavior at compile time through subclassing, extending a class, and instantiation. With delegation, though, an object's behavior is derived at runtime. And the way this works is each object has a prototype. So if you send an object a request for, say, a property or to invoke some behavior, the object will respond to that request if it can. If it has the property defined locally within it, for example. Otherwise, it will delegate its request to its prototype. And the prototype will then look at that request and see if it can handle it. If so, it will. Otherwise, it will delegate it to its prototype. And this process can continue all the way up the prototype chain until we either find a prototype that can respond to the request, or we have no more prototypes, in which case we return null or some default value. This idea of delegation is not new. Henry Lieberman wrote the original paper in 1986. If you're familiar with JavaScript, you notice that each JavaScript object has a prototype. So you see that in JavaScript. When people need to do some sort of taxonomy in a language like C, they'll use a delegation. So if you're familiar with X Windows, for example, which goes back quite a while, but they use the same kind of concept there. So having established the background for the talk, what I'm going to do is first show how delegation can be used to build a solution that when viewed from the outside looks like inheritance and can solve some of the same problems that inheritance is good at solving. Then I'd like to examine delegation further and see what else we can do with it. And in particular, look at how it can address a problem called incremental learning. So the first example we're going to look at is a simple shapes taxonomy in which the concrete shapes inherit or seem to inherit some common behavior from an abstract superclass called abstract shape. All this code I'm going to show you in this presentation is in the Go language. If you're not familiar with Go, don't worry. I have about a month's experience, so you're in very good hands. Let's take a look. Here is some Go code. So this is an interface called shape. So we have three functions here. I will probably use method and function interchangeably, but in Go, the correct name is function. So the location function returns the location of a shape, which could be the center of a shape or it's for one of its vertices. It's up to the shape subclass to determine how to interpret that, or the type that sort of plays the role of the shape subclass. Then we have a move function that translates a shape, its location by a given x and y offset. And then there's a resize function that will change the area of a shape based on the given size ratio. So for example, if I give a new area ratio of 2, it's going to double the area of the shape. Now in Go, any type that implements all three of these functions is said to implement the shape interface. You don't have to say this type implements shape like you would in Java, for example. It just does. Go just knows that it does. So let's take a look at the abstract shape here. So here's an abstract shape. Now, and this is a type struct. If you're familiar with C coding, this is a type def struct. It's the same thing. So the only difference with Go and C is that in Go, we put the name of the object first in this type. So we have an abstract shape, which has a location. And we have a function that returns that location. Now, if you notice, after the func keyword, there is this declaration in parentheses of an abstract shape called A. In Go, this is referred to as a receiver. What that means is I can actually call the location method on an abstract shape instance. And now, normally in a language like Java or C#, you would not be able to instantiate this abstract shape because it's an abstract class. In Go, we can instantiate this, and in fact, we will do exactly that in this example. And then you see the move method, or see, I know I would use method, move function. And notice there, abstract shape has an asterisk before it. That's a pointer dereference. It's a way of saying in Go that this is an output parameter, and we move the location. Now, here we notice that there is no resize function because resize is not common functionality. It's up to each shape to define a resize. So this abstract shape type does not implement all the functions of shape. Therefore, this cannot be assigned to a shape variable. Now, like in Java, again, we couldn't even instantiate an abstract shape because an abstract shape does not stand on its own as a shape. In Go, we can instantiate this, but we cannot assign it to a shape. So it's another way of saying the same thing. It's analogous to the concept of an abstract class. Let's look at a concrete shape. So we'll choose rectangle here. We scroll up to get to the top of this. So here we have a structure. We have a width and a height, as you would expect, and there is a reference to an abstract shape. That is the prototype of this rectangle. Now, notice that I did not name this abstract shape. There's no object name here, just the type reference. That's because Go will automatically handle delegation when it's done like this. So, for example, you notice that there is no move method or move function or resize function. No move function or location function here. That's because abstract shape handles that. Now notice on line 36, I'm actually calling location on a rectangle. So Go is going to automatically delegate that function call to abstract shape. So between rectangle and abstract shape, we have all three functions implemented. Rectangle implements resize, abstract shape implements move and location. Therefore, this is assignable to a shape. And we'll go ahead and look at the circle. Those are the only two concrete shapes that I have. Circle, we have a radius, but otherwise the same thing. Now, one thing I do want to point out, line 13, there's a function called new circle that returns a circle. There are no constructors in Go because there are no classes. So good practice is to create a function called new and then the type name that will return an instance of the type. So when you're building types in Go, that is a good practice to follow. Now I'm going to show the shape demo app here. All right. So line 9, we create an array of 4 shapes, and notice on the next 4 lines, we assign circles and rectangles to those shapes. So because circle and rectangle with their abstract shape prototypes help implement all 3 functions, I can do this. The key to this code is look at lines 18 through 21. I'm calling move on a shape. Now remember, none of these shapes, the circle and a rectangle, have move implemented locally. So Go is going to delegate that to the abstract shape prototype. Then I call resize on line 27, which illustrates the runtime polymorphism that Go can support. Don't need delegation for that. Then I print out the shapes. Let me run this just to prove this actually does work. That's not just code. It should be, there we go. And so we have just printing out the shapes before it's constructed, after the moves, and after the resizes, and you can see various properties have changed. So what we've seen here is that delegation can exhibit a semantics that when viewed from the outside looks like inheritance. So I have this move function I can call. I mean, from the outside, it looks like this shape inherited move from some sort of common superclass, but that's not what happened at all. Obviously, it delegated move to its prototype, but it kind of looks like inheritance. You can have some of the same kind of behavior. One thing we use inheritance for is to factor out common behavior. I think inheritance is often abused in that way, but here we're using delegation to do exactly the same thing. It has exactly the same semantics. I'm going to pause a bit here and ask if we have any questions.
I think everyone is still getting their coffee into them and waking up this morning. We don't have any questions yet.
Okay, I'm not sure I'm going to be much of a help for waking up, but I'll do my best. All right, I'm going to switch back to the presentation now. So far, all we've done is go through a delegation pattern in which each object has its own personal prototype. Now, that is undoubtedly the most common way that we use delegation. It's in fact, it was the topic of the Lieberman paper that started this, is how do we factor out common behavior where we don't have inheritance. But that's not the only way that we can use delegation. There's actually another pattern in which multiple objects share the same prototype. So I call this the shared prototypes pattern. So why would you want to do this? Well, to answer that question, let's take a step back and talk about how inheritance and delegation represent the acquisition of knowledge. So an inheritance hierarchy is the result of deductive reasoning. So for example, if I have a taxonomy of animals of some sort, and I know that a dog is defined in the taxonomy as a mammal, having a snout, a tail, and 4 legs, and I know that Rover there's an object named Rover that's an instance of dog. Well, I know that Rover also has a long snout, a tail, and 4 legs. I know this because Rover is an instance of dog, and dog has those characteristics. So we can think of class as a set that defines the characteristics of all of its members. So if we know that an object is a member of a set, we know everything we need to know about that object within the context of the system that we're modeling. There's a lot of power in this. First of all, it provides a solid mathematical foundation for inheritance, but also gives us the ability to reason about the semantics of a program before it runs. And that's a pretty good thing to be able to do. But what if you don't know our taxonomy ahead of time? Or what if our taxonomy is going to change quite a bit? I actually worked on a system when I was at NASA that did this. It was a planning system where astronauts were given tasks and they could create their own schedules. They had a task taxonomy for the astronauts, but that was going to change during the mission, which could be months and months long. And so they had to have the ability to change this on the fly, their taxonomy. Shared prototypes allows us to do this. So this shared prototypes pattern gives us another way to model the acquisition of knowledge. We can model incremental learning by generalizing from instances. So instead of defining sets ahead of time and then creating members of those sets that have all the properties associated with the set, we start with members and we start reasoning about the members to derive the characteristics of a set that they could belong to. This process reflects how we learn. We all learn like this. We learn from instances. We learn long division by doing 70 or 80 homework problems every night. At least I did. And after a while, you can generalize the process from all those instances. So that's how we learn. So instead of saying that an object is an instance of a class, in delegation, we say that an object is similar to a prototype. So for example, if you're familiar with the work of Ludwig Wittgenstein, he has an example called games. Now, if I were to ask you to give me a list of properties or characteristics that all games have in common, you're not going to be able to do it. I've tried. There really isn't a single property that all games have in common, unless it's a very, very generic thing. But we know that certain activities are games and certain activities are not games. We kind of know what a game is and what it isn't. So what Wittgenstein said was activities that are games have a family resemblance to other activities that we've already determined are games. That family resemblance is the prototype relationship in delegation. And so this models how we learn. Now, I need to point out prototypes and objects are the same kind of construct. So in delegation, there's no class instance distinction. An object is an object. A prototype is also an object. A prototype is simply an object that some other object is using as a prototype. Otherwise, they're the same. So delegation allows us to build and modify a taxonomy from the bottom up dynamically at runtime as new facts become available through inductive reasoning. So inheritance is deductive reasoning, delegation is inductive reasoning. So I'm going to go through another example of this. We're going to build an animal taxonomy from the ground up, starting with instances. I'm going to show this on the slides first, and then I'll take you through some code. So there are 4 taxonomic operators that we're going to use to do this. So the first one is object addition. We simply add an object to the taxonomy. We can also state which object already in the taxonomy is this object's prototype. Object update allows us to add properties to an object or modify existing properties. Fairly straightforward. The next 2 are not as straightforward. I will go through them briefly here, then I'll show you some examples later that hopefully will make these easier to understand. Promotion creates a new prototype based on one or more existing objects. And so we will take the intersection of the properties of those existing objects and pull those up into the prototype. Then all the existing objects now point to the new prototype as their prototype. And the distribution allows us to push some of a prototype's properties down into its immediate instances, those that have the direct prototype link to the prototype in question. This is kind of a way to make a taxonomy more symmetrical. So I'm going to just leave that there, and then when we go to an example, I'll show it in more detail. So let us follow the adventures of a young girl named Marissa as she goes to the zoo for the first time. Now she enters the zoo, all she knows is there are animals there. That's it. She's going to see some animals and she's going to build up a taxonomy of animals in her mind. Now she enters the zoo, she sees Stanley the Komodo dragon. So at this point, all she knows is Stanley is an animal because she knows animals are in the zoo. Stanley, that's an animal right there. So she uses object addition to add Stanley to her taxonomy as an animal. Animal is Stanley's prototype. Now she can observe that Stanley has no hair and she's told by her parents that Stanley is cold-blooded. So she uses object update to add those two properties to Stanley. This is what our taxonomy looks like right now after seeing one animal. So next, Marissa and her family walk over to the elephant enclosure, which is pretty close by. And she sees Clyde the elephant. Now she can look at Clyde and see that he's got a little bit of hair, not a lot, but some. And she also can see that he has a long trunk and he has tusks. And she's also told by her parents that Clyde, unlike Stanley, is warm-blooded. So she uses object addition to add Clyde to the taxonomy with animal as its prototype because that's all she knows right now. Clyde is an animal. It uses object update to add those four properties to Clyde. Now she's looking around, she's very excited, obviously. It's her first time to the zoo, lots of things to see. She's looking around and she sees in the distance this really tall animal with a very long neck that's peeking up above a fence. And someone tells her, that's Jerry. And she can see Jerry has hair. He's got a long neck. And she's told that Jerry also is warm-blooded. So she uses object addition and object update again to add Jerry to the taxonomy as an animal with those properties. Now, as Marissa is talking with her parents about all these animals she's seeing so far, she's told that Stanley is a reptile. So she's going to use the promotion operator to make this new prototype. So what's going to happen is she's going to use promotion on Stanley to create a prototype called reptile. Now, we're only using Stanley as the one object example. So we're going to take both properties that Stanley had, and we're going to pull those up into the reptile prototype. So now reptiles are cold-blooded and don't have hair. And Stanley is a reptile. So if you ask Stanley what his prototype link is, it points to reptile. So now, if you ask Stanley whether he has hair, he can't answer that question directly. He's going to delegate that to his reptile prototype, and that will answer false. Stanley has no hair. And also, Marissa finds out that Clyde is an elephant and Jerry is a giraffe. So we do the same thing. We use promotion on each of those two animals to create those two prototypes. Their properties are pulled up into their prototypes. Now also need to mention that when we do this promotion approach, the prototype of the new subtype we created, for example, the prototype of elephant is the prototype that Clyde used to have. So before the promotion operator was applied, Clyde used to have animals as prototype. Now that he's got elephant as a prototype, elephant will take animal as his prototype. So the promotion is how we create subtypes. And so right now we have three animals. We have three different types of animals in this taxonomy. Now, it's important to point out at this point that if you ask Marissa to describe an elephant, what's an elephant? She's not going to describe some generic elephant. She's going to describe Clyde. Exactly. If you ask her to describe a reptile, she's going to describe Stanley, not just some generic reptile. Because she doesn't know what a generic elephant is, or a generic reptile, or a generic giraffe. She just knows the one instance of each. Those instances are her class definitions. That's how we learn. If we see one instance of something, and that's all we know of it, that's our class. We will change over time as we see more instances. This is how we learn. And the cool thing about this with delegation is we can model this learning process in software. Now, next, Marissa notices that elephants and giraffes have something in common. They're both warm-blooded, and they both have hair. So she finds out also that animals like this are called mammals. So she applies promotion again, this time to elephant and giraffe to create the prototype mammal. Now, when she does this, what happens is the warm-blooded property and the has hair equals true property are common to both elephant and giraffe. Those two properties, that intersection of the property sets of Clyde and Jerry, get pulled up into the mammal prototype. The other properties, the elephant properties that are unique to elephants, and then the long neck property unique to giraffes, stays with their prototypes. It stays where they are. So now we have mammals with two types of mammals. Now, Marissa is fascinated with elephants, and Clyde in particular. She wants to stay there for a long time and just watch the elephants. She just loves it. So she stays around for a while, and she notices that another elephant comes out named Chloe. Now, Chloe doesn't have tusks, but otherwise she looks a lot like Clyde. So she doesn't think much of this at first because, I mean, maybe Chloe got sick and that's how she lost her tusks, or maybe someone snuck in at night and stole them. So that's why she doesn't have tusks. So it's just a one-off. So she adds Chloe to the taxonomy as an elephant. It just adds the has tusk property equals false to her. But then a few minutes later, Claire walks out and she doesn't have tusks either. Well, at this point, Marissa knows that, you know, this tuskless elephant it's really a thing. It's not a one-off. So she's going to apply promotion to both Chloe and Claire to create an elephant subtype called elephant without tusks. As Chloe and Claire both have the has tusk equals false property in common, that gets pulled up into the prototype. So now we have a subtype of elephant. Now, Marissa likes the tidy taxonomy, and who doesn't? So she decides that, well, if you're going to have an elephant without tusks prototype, we need to have an elephant with tusks prototype as well. So she uses promotion on Clyde, applies that operator to get an elephant with tusks property. Now, at this point, the slide doesn't show this right now, but right now, has tusk equals true actually still belongs with elephant, because that's where it was put when we applied promotion to Clyde to create elephant. So it's kind of doesn't, if has tusk equals true is with elephant, then the taxonomy is kind of asymmetrical, right? You got one subtype about tusk that has a has tusk property, another elephant with tusk subtype that doesn't have a has tusk property. Kind of doesn't make sense. So she's going to use the distribution operator to push that has tusk property down into elephant with tusks. And so the way this works is we look at the two properties that elephant has at this time, which are has trunk equals true and has tusk equal true. Now, neither elephant with tusks nor elephant without tusks has a has trunk property, so we're going to leave that with elephant. They're all going to answer the same way if you ask them whether they have a trunk, so we can keep that at the prototype. But elephant without tusks has a has tusk equals false property. Elephant with tusks does not have a has tusk property, so we're going to push has tusks from elephant down into elephant with tusks. So now we have a pretty nice taxonomy here. So we have a nice balanced taxonomy with respect to elephant. We have an elephant without tusks whose has tusk property is false, and an elephant with tusks subtype with has tusk equals true, which is what you'd expect to see in a taxonomy like this. So through looking at 5 animals, Marissa has built this taxonomy in her mind, built it from the ground up. It's a pretty nice taxonomy. It is quite valid, just from looking at instances. So let's take a quick look at the code. I'm going to share this one. So this is the code that is used to back this example. This is a very generic taxonomy app, basically. So I know we're talking about animals in our example, but the fundamental type is called object. So object has a name, obviously. It has a prototype. Now here, I'm actually having to name the prototype, unlike the first example, because Go does not handle this shared prototypes pattern by itself. So I have to do it myself. I have to actually do it manually. So I need a handle for the prototype. So this prototype is an object, just like this object is. So prototypes and instances are exactly the same thing in delegation. They're the same kind of thing. And there's a property map, simple map string to interface. And Go, when I say interface with just the curly braces, that's like an object class in Java. I forgot what the root class is in .NET. It's the same, or C#. It's the same thing. It's basically the top class in the inheritance taxonomy for that language. So a property map is essentially a map of string to anything. So I've got my new object. Following good practices, I can instantiate an object this way. I can get and set the name, but look at the get function on line 21. I can invoke this on any object. And the first thing I do is I check to see whether this object has that property. If it does, great, I return it. If not, I get that object's prototype. If it has a prototype, I'm going to invoke the get function on that prototype. And then the prototype will do it. The prototype's an object also. So it's going to do exactly the same thing that this did. So for example, if I ask whether, say if I ask whether Clyde has a trunk. So Clyde looks for trunk in the property map, it won't be there. So it looks for its prototype. There is a prototype called elephant with tusks. It will call get on that object, elephant with tusks. It also does not have that has trunk property. So it will forward the request to its prototype, which is elephant. Elephant does have that has trunk property in its map, and it will return the value true. This can go all the way up the chain. And we also have a set function. We can set a property. Once this happens, either we have a new function, new property that's associated with this object, or we can override the value of a property for the prototype. So we can override a property's prototype using this with the set. If I set a property, the next time I call get on that property name, it will be in the object's local property map and it will return it directly. I can also unset a property. This basically just means I want to go back to what the prototype says. And then we can get the property map and then we can set a prototype and so forth. There's an instantiate function here. We haven't talked about it because we don't need it in this example. You can instantiate a prototype. All it means is, or instantiate an object actually. And all it means is we create a new object whose prototype link points back to this object. And so if the object that we're instantiating is not a prototype, it becomes one just by having a prototype link pointing to it. So anybody can grow up to be a prototype in delegation. Okay, so that's objects. So I'm going to take a look at these operators that we talked about. So let's start with object addition operator. Each one of these operators has an apply function that takes a taxonomy as input, and it returns the modified taxonomy as its return value. So for object addition operator, I'm going to create a new object with that name that I have associated with the operator. I'm going to see if there's a prototype name. So in line 23, you can't set a string to null and Go as far as I know. So to check whether the string has a value, check that its length is greater than 0. I could be wrong there, but I think that's how you do it. So if there's a prototype name associated with this operator, I get that object from the taxonomy. So I haven't shown this taxonomy class, but basically I can get an object by name, and that's what I'm doing here. If the prototype name, it does have an object associated with it, then I set this object prototype link to point to that. And then I add the object to the taxonomy and then return it. So that is object addition. Let's look at object update. The second one we talked about. It's pretty straightforward. So it has an object name and properties, which are an array of properties. So in its apply function, I get the object from the taxonomy by that name, assuming it exists. I'm going to loop over the properties. So in Go, what this for loop does, when you range over an array in Go, you use two objects there that you're setting. The first is the array index, the second is the array value. I don't need the array index here, so I'm going to put an underscore as a placeholder. That's not optional. If I put the array index there, that would be an error because I have an unused variable. So I don't want to use the array index, so I put an underscore there. And then for each property, I simply call set on that object and set the property, and then return the taxonomy. So pretty straightforward there. So what is not as straightforward is next two. So I'm going to try to go through those in a little more detail. Promotion. So promotion operator takes a prototype name and then a list of object names that I'm going to use as the basis for creating the prototype. So the way the apply function works here, and this is not the most understandable code ever written. I kind of hacked this together over the last week or two, so I apologize. I will spend some time in the near future getting this code into a better shape that makes it easier to understand. Right now I have to talk this through and it might be a little bit difficult to figure out. So first I'm going to create a prototype because that's a new object that has the prototype name that was given. Then I'm going to get the objects that were mentioned as the object name. So for example, if I call this on Chloe and Claire, and the prototype name is elephant without tusks, the objects I retrieve on line 29 are Chloe and Claire. So I'm going to loop over those two objects, or the objects that are in that object name list. And I'm going to build an intersection of its properties. That's what I'm trying to do here. So I'm going to lines 30 through 37, build the intersection of the properties of Claire and Chloe. So once I've done that, I'm going to set those properties on the prototype. Then I'm going to take on line 39 the object's original prototype, which in this example with Chloe and Claire was elephant. I'm going to set the elephant without tusks prototype to elephant. That's what line 39 does. So now I basically inserted this prototype into my taxonomy as a subtype. Then for each of those objects, I'm going to remove the properties that were in the intersection. So once I've done that, I have now pulled those properties, those common properties, into the prototype. Then I'm going to set each object prototype link to the new prototype I just created. Then I'm going to add the object to the taxonomy, the new prototype. That is promotion. So hopefully you can follow that. That's not the easiest code to look through, I understand. I apologize for that. And then distribution. So here, the example we had was, we had elephant with the property has tusks equal true, and we wanted to push that down into elephant with tusks so that the elephant with tusk and elephant without tusk prototypes both have that has tusk property. So I'm going to get the prototype, which is elephant in this example. Then I'm going to call taxonomy.getInstances to get the objects who have a prototype link directly to that elephant prototype, which would be elephant with tusks and elephant without tusks in this example. Then I call distribute properties. It calls on line 30 get properties to distribute. This will find properties that are possessed by a proper subset of the instances. So if every instance has this property, it won't make the list. If none of them have this property, it won't make the list. Only the ones that are possessed by a proper subset of those instances. So in our example, that was has tusk equal true. That would be the property we're going to distribute. So then for each of those properties, in this case 1, I'm going to arrange over the instances. If the instance does not have this property, I'm going to provide that property. So as a result, I'm going to push that property into the instance on line 34. Then I'm going to remove it from the prototype, line 35. So now I have pushed the property into the immediate instance. In the example that I showed on the slide, we now have a symmetrical taxonomy where elephant with tusks and elephant without tusks both have the has tusk property. Okay, now I'm going to show you some test code here. And Go, any source file that ends in underscore test.go is a test class or test type. Any function in there beginning with the word test is designated as a test function. So you see how IntelliJ has decorated that test simple animal taxonomy function. This is probably the only code this example is somewhat well written because you can actually follow these examples. Each of these function calls follows one of the slides I showed you in the example. And if we go to these different functions, we can see the operators that we're applying to the taxonomy with their arguments to perform each step. And so we have these, I think, pretty much in order. So you can see in this code how we actually make that taxonomy happen, how we make those taxonomic changes happen through our delegation code. So we have a number of these. So I got one for each slide. Then we're going to generate a file. That's a plant UML file. So plant UML is a utility that I can give it a UML file and it will generate a UML diagram from that file. So I'm going to do that so that we can see which taxonomy was created from this code. I've got a bunch of assertion tests that I'm doing at the bottom here. So let's run this. Take a few moments to do so. There we go. All righty. And then I'm going to look at this taxonomy.puml file. This is the plant UML file that I generated. So on the left, you see this is the contents of the file that my code generated. This is a bunch of styling stuff. And then you see starting at line 13, the objects defined and their properties. Starting on line 33, these are the prototype links that we found in our code. Let me zoom in here on this diagram so you can see it a little bit better. As you can see, this is the prototype. This is the taxonomy that was generated in this code. And it's the exact same taxonomy that we saw on the slides. I mean, it doesn't look the same. We don't have the cute clip art, but we have animal with mammal and reptile subtypes. Stanley is a reptile. Mammal has the elephant and giraffe subtypes. Jerry is a giraffe. Elephant has the elephant without tusks and elephant with tusk subtypes. And we have Chloe and Claire is elephants without tusks, and Clyde is an elephant with tusks. So this code generated that taxonomy that we showed on the slide. So we have just used the shared prototypes pattern to build up a taxonomy at runtime dynamically through incremental learning. We have just modeled an incremental learning process that is a rough analogy to how we learn things, which I think is pretty cool. Now, one thing I do need to point out is that this is a runtime taxonomy. And so the consequences of that are, if I change a property somewhere in this taxonomy, it can have immediate effects. For example, if I go into elephant here, and I decide to set has trunk equals false, immediately Chloe, Claire, and Clyde lose their trunks, just immediately. This happens at runtime. So whenever, in general, when I change the property of a object in the prototype, it can potentially affect the transitive closure of that object with respect to the prototype relationship. So in the case of elephant, if I change has trunk to false, it can potentially affect 5 objects that are underneath it. The transitive closure of that object with respect to prototype. Now, this may be what you want. For example, I may decide that for each of these animal types, I'm going to also have a property that indicates what section of the zoo I can find these animals in. So maybe elephant has section equal to 1. And then maybe I've built a new elephant enclosure somewhere else in the zoo in section 6. I could change elephant's section property to 6, and suddenly every elephant, if you want to know where they are, it would say they're in section 6. So it could be what you want to do this kind of runtime property change that affects a fair amount of your taxonomy, but just be aware that that can happen, that you can actually affect many different objects in this taxonomy with one property change. The delegation comes with flexibility and adaptability, but with that comes responsibility. And that's a lot of abilities in one sentence. Back to the slides here. So in summary, there are a couple of takeaways from this presentation, and they are the following. Delegation enables you to build solutions that have the appearance of inheritance, even when inheritance is not available in the language you're coding in. And we saw that example in the first example. We were able to factor out common functionality into separate objects and make it look like that common functionality was being inherited by the concrete shapes from the abstract shape type. So in a language like Go or C, if you want to build some sort of inheritance hierarchy, you can do that using delegation. And then second, even if inheritance is available, regardless of whether it's available or not, delegation provides the flexibility to model knowledge that you acquire through inductive reasoning. And as we've seen, that's a very powerful thing. I think it's pretty cool. So you can use delegation is a good thing to use even if you have inheritance. If you don't have it, you can use it to build something similar to inheritance that looks and performs in a similar fashion. All right, I'm going to pause here for see if any questions have arrived.
Yes, Michael, it does look like the coffee's kicked in and we've got quite a few questions.
Okay.
So I'm going to break these up in a couple of areas. Let's start with just some questions about Go itself.
Okay.
The first one being, does Go have the concept of mix-ins?
I don't think it does. I'm not sure though. I have to look that up because like I said, I have like a full month's experience in this language, so I'm not an expert in it. I don't think it does. I mean, using what we did with delegation, you could implement that, right? You could have multiple fields in a struct and implement mix in yourself. But I don't think Go will do it automatically.
Okay. The next question, what's the scope and lifetime of objects in Go? And is dependency inversion possible?
Man, they're asking the tough questions. I think you can do dependency injection in Go, but I don't know how to do that. We haven't had to do that for the code I'm writing at my client. The scope of object, I think, is pretty similar to what you think of in other languages. So it's based on the declaration of it. So like in the case of those types I had, it would be the scope would be that type and any functions that are defined with the receiver on that type. If you define an object inside of a function, it has a scope of that function. If you define like in that loop those for loops I showed you, any object I declare there will have a scope of that loop. Now in Go, if I set a variable equal to something, I must have declared it first. If I set a variable to colon equal something, as you saw in some of those examples, then that's basically like doing we call it static type inference situation. But in that case, that's what I did in the loop, for example, and then those variables have the scope only of that loop. Once the loop is finished, those variables go away.
Okay. How would you implement multiple inheritances with prototypes and delegation?
Okay. So multiple inheritance. So the example I have here, where you just have a property map, I would likely have to have multiple prototypes. You could have, we talked about an object sharing a prototype. You can also have an object with more than one prototype. And so in that case, you would query each prototype you have to see if one of those could actually respond to that request. So that would be one way to do it. And you could do this through using a chain of responsibility pattern. We just go through the list until you find one prototype that can respond, or maybe you give all the prototypes a chance to respond and then decide which response you're going to accept and return as the result. But I think using multiple prototypes is how you would do that. I did an example a long time ago when I was at NASA, multiple inheritance using delegation, and that's how I did it with multiple prototypes. Unfortunately, I don't have that code anymore, but I know you can use multiple prototypes in the same object to simulate multiple inheritance.
Okay, thank you. Here's one that's a little bit more about you and your journey in learning this. Where did you get started learning about Go? From golang.com, or could you recommend other references you used for starting to learn?
I started with golang.com is where I went. So I went to the Golang website. There's also a website called Effective Go. I don't have the URL memorized, but that was another website that I used. So those two primarily, Golang's website and then Effective Go website.
Thank you. For the attendees, we have about 5 minutes left in our presentation slot. So if you have any further questions, please go ahead and get them in, and we'll try to address them as quickly as we can. In the meanwhile, there's one that's a little bit off topic, perhaps, but this one's from Kevin. He says, would you consider the way that Marissa increases her understanding of the different animals shown to her to be similar to how an AI learns? As in, the machine doesn't understand what it's shown, but will use the promotion delegation style of learning to create a hypothetical understanding of what's being shown?
That's an awesome question. And I think you could. So, because one of the problems in machine learning are classification problems. So I know given a taxonomy we have, you could use classification problems to say, hey, this object looks kind of like one of these other objects, and I'll make the prototype link there. The interesting thing becomes, as Kevin pointed out with promotion, where you're having to assert something that's similar to something you haven't seen yet. And so, I mean, you may have a threshold of like how similar does a new object have to be to some existing subtypes to make a prototype link. If it doesn't meet that threshold, we're going to create a new prototype. I think absolutely this is something we could do with AI. I can see using this kind of approach to build a taxonomy ahead of time. If you needed to have some code, for example, that has an inheritance hierarchy, but you don't know what that's going to be yet, you might be able to use a machine learning algorithm like that to go through existing instances and create one. And obviously, I don't know how exactly that would be done, but I think you can absolutely use AI to, in conjunction with this approach, to build up a taxonomy. That's a great question.
Well, with that, I think we are about ready to wrap it up. So thank you all for attending today's session. And Mike, thank you especially for sharing with us. This recording of this session will be available later at houstontechfest.com. We hope that you enjoy the rest of Virtual Houston Tech Fest today. Have a great time. Bye.